Okay, so I am going to be trying to understand this equation here for which relates quantities expressed in a inertial frame S to quantities known in a non-inertial frame S prime rotating with respect to S at a constant angular velocity omega. So this is mainly for me to try and understand this concept because I've been having some difficulty with it. This is the first attempt and the last attempt at a video. This is not going to be super high production quality. So just so that we're all on the same page, the exact system we're dealing with is we have an inertial frame. We'll say the Earth, even though that isn't really inertial. I'm sitting on the Earth, and I'm inertial. I'm in frame S, and we have a non-inertial frame S prime rotating with respect to that at angular velocity omega. In S, we have a set of basis vectors E I hat, so E1, E2, E3, and in S prime, we have a set of basis vectors E I prime hat. Okay, fantastic. Now, a lot of my confusion in the past has come out of weird notation. So I'm going to try and describe very explicitly what my notation is. So if I express something like this, okay, so first let's talk about A. A is just a vector. It is a geometric object. It exists completely independent of any basis. I can write A as AI EI hat. Yep, okay, I can express A in the S basis, or I can write it as AI prime EI prime hat. So I can express it in the S prime basis as well. Now, when I talk about square bracket A sub S, I'm talking about something totally different. What I'm talking about here is the mathematical object of the vector expressed in the EI basis. So this here is A1, A2, A3, okay? And this is not equal, in my notation, to this, because the mathematical object that is the vector A expressed in the S prime basis is not equal to the mathematical object that is the vector A expressed in the S basis. We would get, two column vectors here, A1 prime, A2 prime, A3 prime, and because entry 1 is not equal to entry 2, entry 1 is not equal to entry 1, entry 2 is not equal to entry 2, etc., these two vectors are not equal. Okay, fantastic, fine. So we have that notation. The last bit of notation that I'm going to use is a round bracket around a derivative. So if I have something like this, what does this mean? So in my notation, this is not equal to that. Okay? This thing here we've described, this would be we take the vector dA dt and we express it in the S basis and we throw that into a column vector. Okay, that's not what we're talking about. What we're talking about here is the derivative of A with respect to time in frame S. So what do I mean by that? What I mean is, for an observer in frame S, what will they think the derivative is? So if we have an observer in frame S, we could write this as dA, an observer in frame S, we'll call this AI EI hat, right? And we can look at dt here, and this will give us dAI dt times EI hat, this is product rule, plus, and this is the bit that I'm explicitly including, plus this extra term here. Okay, so an observer in frame S thinks this is 0. They think that the derivative of their position vectors with respect to time is nothing, right? Their position vectors aren't changing. They're in that frame. So when I write dA dt with respect to S, what I mean is this. I mean dAI dt ei hat, because they think this bit is all gone. Okay, so now that we have some notation here, we are ready to actually talk about this equation. And I should find a better way to erase things other than Command Z. Well, okay, so we've run out of Command Zs here, so we'll ignore this for now. To derive this equation, I'm actually gonna set A to be R, the position vector of some object, and I'm gonna do this because I think it helps ground it a little bit in, okay, I know what this vector is, but every step we do here can be done with an arbitrary vector A. But I'm gonna stick with R, and you can replace the R's with A's in your mind if you want. So let us consider first, we'll start with the left-hand side, and we're gonna be looking at dr dt in the frame S. This is the non-rotating frame. Okay, well, we can write R, we know we can write R as r I prime. Actually, I'll write this as xi prime, the ith component of the position vector, times ei hat prime. Yep. Okay, this is fine. And we're doing this derivative in the frame S. So we've expressed R in the frame S prime, and we're taking a derivative with respect to the S frame. Great, fantastic. So product rule, no problem. So we have dxi prime dt with respect to the frame S times ei hat prime plus, and product rule, d ei hat prime dt with respect to the frame S. Okay, so now up above, what we did when we talked about this derivative with respect to S, derivative with respect to S prime, the only difference there was when it came to differentiating the basis vectors, the vector components. The derivative with respect to a scalar, dxi prime dt, is a scalar. That's right up here. This is just a scalar. And regardless of what frame you're in, you agree on derivatives with respect to scalars. So this is just equal to dxi prime dt with respect to no frame, right? It's the same as with respect to S prime. It's the same as, so I'm just going to write this here as xi prime dot, right? It's just it's a derivative with respect to a scalar, no problem. ei hat prime. Okay. And then we have this thing over here. So at the moment I'm just going to leave this second term. And at least for me, this is sort of enough. This is what I came to look for. dt s. Okay, now here, this thing here is, and I'll just write it, but I don't think it's too crazy. This is dr dt with respect to S prime. So how do we know that? Well, one way that we could sort of show this to ourselves is if we just quickly look at what is R. R is R prime. Sorry, we decided we are going to say xi prime ei hat prime dt with respect to S prime. If we do product rule, we're going to get a first term, dxi prime dt times ei hat prime. That's what we have here. And we're going to do a second term, and the second term is going to be, so we have first term, plus, and the second term is xi prime times dei hat prime dt with respect to the frame S prime. But we know that with respect to the frame S prime, they think their own basis vectors aren't moving, so they think this is 0. And so we have that this big derivative with respect to S prime is just equal to the first derivative of the position times the basis vector. Okay, wonderful. So what we have here, this bit is dr dt in S prime. And the second bit, and this is where I feel like I have less insight. okay, I can just straight up tell you, I can say this is omega cross R. You know, there are other videos you can watch to figure out why this is it. I don't have a super clean one, so I'm not gonna try and explain that here. But just completely informally, it's not completely crazy, right? If omega is really high, we know that the rate of change of the basis vectors is going to be higher. Okay, so we need some omega dependence. We need some R dependence. We already have that here. That's fine. It's not a derivative of R. And we know that if I have my EI here, I'll write E1 here. Let's say E2 is here. And we have E1 prime. So let's say it's rotating like that. The rate of change of E1 prime or EI prime, the vector there, the velocity vector we could say of this basis vector, is going to be perpendicular to EI prime. So E1 prime. So we know E1 prime dot is sort of perpendicular, right? So perpendicular to the first basis vector, that's where we get the cross product, and we also sort of know it's going to be perpendicular to omega because it's rotating around omega, right? Omega would be coming out of the page if we were going here. Okay, fine. So we get this omega cross R. You can absolutely be more formal and get this explicitly, but for me at least, this is actually what I'm looking for. dr dt with respect to s. Okay, fantastic. And the last thing I want to talk about is sort of some notational problems that I have seen come up. So I think with the notation I have used, I have satisfactorily, at least for myself, shown this result to be true. And then you can sub things in and derive other stuff like the Coriolis forces and such. The problem I see with notation is we defined notation like this earlier on, and we didn't actually use it. And the reason I define it is because I see it everywhere, and I don't really know what it means because it doesn't mean the same thing. It doesn't mean the same thing as this. So be very careful. What I am not saying, I am, for example, not saying this is true. I'll put a not equal there. Plus omega cross A. Okay, that's not what I'm saying. Because this would be, we take the derivative with respect to time of A, which sort of already needs a subscript, but okay, fine. And then we look at the mathematical object of that expressed in the S basis, and then we do the same thing and we express it in the S prime basis, and then we can add stuff to those column vectors. We add omega cross A and they become equal. And that is not true. I don't believe that is a useful result. So okay, maybe I'm wrong there. This is places where I'm less certain. But what I do feel pretty confident in is if we use this notation, what I've derived here makes sense for me.